let's look at problem 841, keys and rooms. For this problem, we are going to share a solution using traversal, either breadth-first search or depth-first search. First, we'll go over the statement of the problem, and then we explain the main method and procedure, and later we write the code and test the generic cases. Let's look at the statement of the problem. So there are n rooms labeled from 0 to n-1, and all the rooms are locked except for room 0. So our goal is to visit all the rooms. However, we cannot enter a locked room without having its key. So when we visit a room, we may find a set of distinct keys in it. Each key has a number on it, denoting which rooms it unlocks, and we can take all of them with us to unlock the other rooms. The question is this: given an array called rooms, where rooms I is the set of keys that we can obtain if we visit that room I, then we return true if we can visit all the rooms, or otherwise return false. So here are two examples. In example 1, all the rooms can be visited starting from 0. So in example 2, starting from 0, we can visit room 0, room 1, and room 3, but we cannot visit room 2. So the return is false. So here are the constraints. The length of the rooms is bounded above by 1000, and the sum of the room's I length is bounded above by 3000, and all the values of rooms I are unique. So with the statement went over, let's look at the method and the main procedure. So from the problem statement, we can see actually this is a standard traversal problem or connected component problem. Basically, the idea and procedure is that we find the connected component starting from 0 or containing 0. Let's call this connected component key. Then we count the cardinality of key and compare with n. So if the cardinality equals n, it means starting from 0 we can visit all the rooms, otherwise not. So before we look at the example, let's make a remark. So if we would like to use breadth-first search, so the container to help is the queue, and if we would like to do depth-first search, the associate container is stack. So now let's look at the example 1 and 2 provided by the problem. So in example 1, the connected component containing 0 is 0, 1, 2, 3. Its cardinality is 4, which equals the total number of rooms, so the return is true. In example 2, the connected component containing 0 is 0, 1, 3, and its cardinality is 3, which is less than 4. It means that we cannot visit all the rooms. So with that went over, let's look at the code. First, we will make it into different steps. In step 1, we are going to build a graph. So for this purpose, let me first track the length information of the rooms array, just for comparison later. And then we initialize a empty graph first. So we use the default dict and use set as container. Then we iterate through the rooms for I keys in enumerated rooms. So we set the value corresponding to the key I as set keys. So here actually we can use list, but using set is easy for check membership. So up here we finish the first step. Now let's look at the second step, that is a traversal hyperfunction. So we can write using BFS or DFS. So here let me first write using breadth-first search, and then we will make a comment on depth-first search. So let's call this function BFS, starting from a room, let's call it I. Then we initialize a set just to track which nodes or which rooms we have already visited. Then we initialize a queue starting from I. Then we began the standard iteration while queue. So we pop the node. Let's see, queue pop from 0. So here the position from which we pop actually determines whether we are using breadth first search or using depth first search. If we pop 0, it's corresponding to breadth first search. If we just use pop, it corresponding to depth first search. So with that said, let's continue. So visited add this new node, and then we check the neighbors of this node for new node in graph node. Then we check if new node has already been visited or not. If it's not in visited, we're going to enqueue this new node. So that is queue append the new node. So with that said, what we want to return actually is the connected component starting from I or containing I. So here we just return visited. So actually we can return the length of the visited, then just compare with the total rooms. So let's return visited in order to review more information later. So with step 2 done, let's do step 3, so return. Basically, we just need to return if the length of BFS starting from room 0 equals all the rooms. If so, we can visit all the rooms, otherwise not. So let's check first the examples. So here for I and case in enumerate rooms, enumerate. So let's check. So it passes the, this is the second example. Let's look at the first example. It passes the first example. Now let's check the generic case. It passes the generic case. Now for the 2 examples, let's print out the connected component so that we know what's happening. So let's print out BFS 0. So let's check it. So for the first example, we see that the component containing 0 is 0, 1, 2, 3. In other words, we can visit all the rooms. So now let's look at the situation for the second example. So yeah, there are one connected component corresponding to 0, that is 0, 1, 3, meaning that we can visit 3 rooms starting from room 0. So we return false. That's basically the solution here. Let's give a quick review, and then you can print out and compare with the 2 examples here. In this solution, we first build a graph, and then we wrote a traversal function. So we can either use breadth first search, so pop from left here, or we can use depth first search. We just use pop from the tail, and then we do the return. And yeah, that's a sort of standard application of the traversal algorithm in this problem. Thank you very much. That's it.